Bismillah ar-Rahman ar-Rahim. As I promised you, we'll solve a simple example on this idea of elasticity and tensile, shearing, etc. Here we have a steel rod is subjected to a stretching force. As you can see, this force is applied along the length, okay? And here we have a certain area. It is the area of the cross-sectional area, which is equal to pi r square, because the cross-sectional area is just a circle, and the area of a circle is just pi r square. The radius is given 9.5 millimeter. The length initially, before the application of the force, was 81 centimeter, and this applied force is 62 kilonewton. The kilo is 1000, so this is just 6.2 times 10 to the power 4 newtons, okay? The length is 81 centimeter, or we can write it as 0.81 meter, okay? And this is the radius, 9.5, 10 to the minus 3 meter, okay? And we are given the Young's modulus and the shear modulus, okay? This is a little bit tricky. For this problem, our object is subjected to a tensile force. For a tensile force, how did we know it is a tensile stress? Because it is trying to stretch the object along the length. So which modulus should we use? Should we use the Young's modulus, E, or the shear modulus, G? Please answer, my student. Yes, you are right. It should be E, because for the tensile, we use the Young's modulus, okay? How do we know this? Because it is a tensile. What is meaning of tensile? The force is compressing our object, trying to reduce its length, or the force is extending or stretching our object, trying to increase its length. Okay, in this question, he would like first to find the stress, calculate the stress. The stress is nothing but the force divided by the area, okay? So stress, which is the left-hand side of this formula, equals the force over the cross-sectional area. The force is 6.2 10 to the power 4 newtons, divided by the area, which is pi r square, and the r is 9.5, okay, times 10 to the minus 3, and the unit here is meter square. If we make this calculation, we'll find that this is 2.2 times 10 to the power 8, 2.2 times 10 to the power 8 Newton per meter square, and this is the stress on our steel rod. Calculate delta L, and delta L here will be the increase in the length because of this tensile or stretching force. Okay, so we need to apply this formula. We have force over area, which we have just calculated, equals E, the Young's modulus, which is written, so we don't use this one. The shear modulus, we don't use it because we don't have a twisting force or a shearing force, okay? Multiplied by delta L over L, as you can see, we'll have only one unknown, okay? So we have force over area equals E multiplied by delta L over L. Okay, we know this force over area, we have just calculated, so we can write this as delta L will be equal to force over area, which is the stress, multiplied by the original length divided by the E, which is the Young's modulus. If you plug in these numbers, you will get 2.2 times 10 to the power 8, okay, which is force over area, the stress, multiplied by the length. What is the length? Length is 81 centimeters, so it is 0.81 a meter, divided by E, which is 2 times 10 to the power 11 Newton per meter square. And here, this one is Newton per meter square, so this unit will cancel with that unit, and you are left with delta L in units of meter, and this will be 8.9 10 to the minus 4. 8.9 10 to the minus 4 meter. Okay, if we would like to write it in millimeters, this will be 0.89 millimeters. This is the increase of the length of our steel rod. Calculate the strain. This is the final or the last question here. What is the strain? The strain, as you can see, it is the change in the length divided by the original length. Okay, so strain equals the change in the length divided by the original length, and this will be 0.89 divided by, of course, this is millimeter, okay, divided by the original length, which is 81 centimeter, but this is 810 millimeter. It should be the same unit, or you can write it as 0.089 centimeter divided by 81 centimeter. It should be the same unit, or you write it in meter, such that you can get the correct. So this will be 1.1 10 to the minus 3. 1.1 times 10 to the minus 3. So this is the strain, or this is just 11%. Okay, 11, not 11%, 0.11%, because this can be written as 0.11 times 10 to the minus 2, or equal to 0.11%. Okay, this is how much the change of the length compared to the original length. طيب, let me take the same rod, but now I'll apply a force from the side, not along the length, but it will be perpendicular to the length. Okay, please take the camera to the other side. So it is the same rod, same length, 81 centimeter, same radius, 9.5 millimeter, same force, but now the force is coming from the side. As a result, our rod will be twisted, and this deflection is delta x. Would like to find how much is this delta x. Okay, now this is a shearing force. So what should we use for the shearing force? I hope this is clear in the camera. Shearing, we need to use the shear modulus, G. Okay, in the case of shearing, we use G, don't use E. So this one we should ignore. Okay, don't use the Young modulus for the shearing. Okay, so we use the shearing modulus, and we write the formula: force over cross-sectional area equals G, which is the shear modulus, multiplied by delta X over the original length. Rewriting this formula, we can get delta X equals force over area, which is the stress, multiplied by L, the original length, divided by G, which is the shear modulus. So force over area, we have calculated this before in the previous example. This was 2.2 times 10 to the power 8, the unit is Newton per meter square, multiplied by L, the original length. Original length is 0.81 meter, divided by the G, which is 2 times 10 to the power 9 Newton per meter square. Okay, so this will cancel with that, and we are left with delta X in units of meters, and the answer here is found to be 0.089 meter. 0.089 meter, or in millimeter, this is 89 millimeter, or 8.9 centimeters. I hope with these two examples you have a good idea about the application of these nice formulas related to the elasticity. With my best wishes. Thank you.